Okay, welcome back. And we are going to pick up where we left off in L'Hopital's rule at the end of the part 1 video. You may notice I did change this problem. I had the problem typed wrong here for what I wanted to do. We're going to do this problem two ways, using conjugates, which we learned way back at the beginning of the semester. We didn't use it a lot, but you should be familiar with what a conjugate is and how to use it, and then using L'Hopital's rule. So first, using conjugates, a conjugate is usually applied to a radical, some set of terms with a radical in it. In our case, we're going to look at the top. The conjugate of the square root of x minus 3 is the square root of x plus 3. Now, why would we do this? Well, if I try to put 9 into my limit, I get the square root of 3 minus 3. I get 0 on the top, and 9 minus 9, 0 on the bottom. I get that 0 over 0 in determinant form. So I need to try something else. In prior lessons, we had learned that we could try things like factoring, which actually you could factor this into the square root of x, the bottom, x minus 9. This may be the way some of you did this, is the same as the square root of x plus 3 times the square root of x minus 3. I actually prefer that to using conjugates, but I'm going to remind you what a conjugate is and do this one using that just for the sake of review too. So the conjugate of the square root of x minus 3 is the square root of x plus 3. So I'm going to transform my original problem, which is square root of x minus 3 over x minus 9, and there were always implied parentheses with this fraction bar. So before I start doing anything to the fraction, I put those parentheses there. I'm going to multiply the top by the square root of x plus 3, because what that will do is I will end up with a negative 3 square roots of x, a positive 3 square roots of x when I multiply this out, and my radical will go away. But I can't just multiply the top. That's changing the value of my function, of my expression. I have to also multiply the bottom. So basically I'm multiplying by 1, and the form I choose is the square root of x plus 3 divided by the square root of x plus 3, because that will utilize the sum and difference of two squares. This is factored. Basically, it's the sum and difference of two squares to give me the first term squared, the last term squared, without a radical on the top. So I still haven't taken the limit, so I continue to write that. And when I multiply out the top, I get x minus 9. You can do that and convince yourself of that. When I multiply out the bottom, it's a little more complicated. I get x square root of x minus 9 square roots of x plus 3x minus 27. I just went through term by term, x, that, and then that times that. So I still have 0 over 0. That doesn't seem to help me any. Well, it could. Because if I didn't, so some of us are saying, well, you multiply that out. Well, I didn't have to do that. I just made my problem harder. So I'm pointing out you don't always initially want to multiply out. When you do multiplication by conjugates, once I see I get the x minus 9 on top, I say, bingo, I've got what I want. I've got a reduction of my rational expression that will eliminate a 0 on the bottom and a 0 on the top. So now, when you do this, you go down a path that isn't productive. Take a look at what you have before you just start blindly multiplying. As soon as I saw x minus 9, I should have realized, oh, I can now reduce. So the limit as x goes to 9 of 1 over the square root of x plus 3 is the same as 1 over the square root of 9 plus 3, which is 1/6. Now, if I do this using L'Hopital's rule, as M says to do in part B, I'm going to take the limit as x goes to 9 of the derivative of the top, and I can do this because I had 0 over 0. Derivative of the square root of x minus 3, well, the derivative of the minus 3 will be 0. Derivative of the square root of x is 1 over 2 square roots of x. That should be pretty well known to you by now. Derivative of x minus 9, derivative of the bottom, simply a 1. So I get the limit, and this should be a goes to, not a minus. Limit as x goes to 9 of 1 over 2 square roots of x, which is 1 over 2 square roots of 9, which is 1/6. Okay, so there's an example using conjugates and how sometimes multiplying out factors. If you're looking to reduce when you multiply out using conjugates. You could have just factored the x minus 9 to this and reduced also, though, and getting the same result. All right, now let's move on to some more examples I want you to try and then come back to the video for. So, take a look at problem 1. Verify if L'Hopital's rule is applicable, if L'Hopital's rule applies, to say that easier. And if not, find the limit using other methods. You may stop the video here, try this one, and come back, and I will do it out. All right. So you're back. So this problem, first I have to see what happens when I substitute. And when I substitute, I get 1 minus the sine of pi over 2 over the cosine of pi over 2. Well, the sine of pi over 2, it's on the y-axis. Pi over 2 is the y-axis, so the sine of it is a 1. I get a 1 minus 1. Cosine of pi over 2 is 0. I get 0 over 0. So L'Hopital's rule does indeed apply. So when I do this, I'm still taking a limit, so I have to keep writing that because I haven't performed that operation yet. I take the derivative of the top. The derivative of 1 is a 0, minus the derivative of sine x is cosine of x. Derivative of cosine x is negative sine of x. So now what I get is negative cosine, I'm taking the limit now, so I stop writing it, pi over 2 over negative sine pi over 2. Well, the cosine of pi over 2 is 0, so negative 0 is just 0. The sine of pi over 2 is 1. I get 0 over negative 1, or 0. This limit is 0. You can confirm that by looking at a graph or using a table. So that's problem 1. Now try problem 2. Stop the video, try it, and come back. Okay, you're back, so I'm assuming you tried it. So first we have to verify if L'Hopital's rule works. Whenever I see a limit problem, my first attempt is to try substitution. Because if this function is continuous at x equals 2, the function value will be the same as the limit. So I try that. And I get 8 over 4, or 2. Oh, I don't need L'Hopital's rule for this one. I can't use L'Hopital's rule for this one because it's not an indeterminate form. The answer is simply 2. Okay, we have a couple more to try. All right, problem 3. Again, evaluate the limit. If you need to, use L'Hopital's rule, verify that it works. And if it does not work, evaluate the limit some other way. So, problem 3. Stop the video and try it. All right, you're back. You may have noticed this is a one-sided limit. The tangent of 0 is 0. And as we come, so the graph of tangent, you might remember, if you're coming from numbers a little less than 0, tangent is negative in the fourth quadrant. Numbers less than 0, tangent is negative for values of like negative, just a little bit less than 0. But it's going to be a 0 essentially. You do get 0 over 0 because if you try just plugging in the 0, tangent of 0 is 0, 0 squared is 0. You can use L'Hopital's rule. So the fact that this is a one-sided limit doesn't really change our technique. I take the derivative of tangent, I get secant squared of x over 2x. Well, secant squared, now I try substitution again. Secant squared is the same as 1 over cosine squared. You're probably more familiar with evaluating cosines. Haven't taken the limit yet, so I keep writing this. So I get the limit as x goes to 0 of 1 over the cosine of 0 is 1 divided by 0. I actually can't use L'Hopital's rule on this at the moment. So I get 1 divided by 0. Not much I can do with that. I can take a look at a graph. I can take a look at, so this is a one-sided limit, so it's possible it goes off to infinity. Because I'm dividing by 0, it either goes off to positive infinity or negative infinity. I can go back and look at the original limit or even look at this version of it here And for both tangent and cosine, if you remember what the graph of tangent looks like, before you get to x is 0, your function values are negative. So you had just a very slight negative number divided by a 0 that would approach negative infinity. So your limit is negative infinity. It's a little review of limits that go to infinity. If I continue to get this division by 0, but the 0 doesn't appear anymore on the top, I have to stop using the L'Hopital's rule. So for cosine, if I used this version of it with the cosine squared, let me change my color of my marker so you can see. So if I looked at cosine squared of x, so I'm looking at 1 over cosine squared x over 2x, and I'm going to look for the limit as x goes to 0 minus there. And again, I can't use L'Hopital's rule because the bottom will be 0, but the top will be a 1. Cosine squared is the same as the cosine of x squared. So that's always going to be greater than or equal to 0. At 0, cosine is approaching 1, so it's not going to be a 0, it's going to approach 1, but it's going to be positive. So even though cosine at values of angles slightly less than 0 is negative, actually cosine is positive at values less than 0. I misstated that. So this is always going to be positive. So I have a positive, but x is slightly less than 0 means x is negative. So I get a slightly negative value here. So that would also, but this value is essentially 0. So it's going to, again, negative infinity. The signs are different. So again, here, this would have been a slightly positive value. I misstated that up here. Because that's squared, no matter what kind of a number I squared, I get slightly positive. So you get differing signs in the fraction. So this one goes off to negative infinity. So that's a review of other ways to evaluate limits when you have division by 0, and your answer may be infinity. If it's one-sided, you do get a limit. With the infinite limits that are infinite, you sometimes can say it doesn't exist if one side goes to positive infinity and the other goes to negative. But this is a one-sided limit, so you know you're going to have either a positive infinity or a negative infinity once you get to this point in the problem. All right. The final example is problem 4. I want you to take a look at this one. Stop the video. Try it. See what you come up with. All right, you're back. So I'm going to assume that you've tried this problem. And actually, I'm going to stop this recording for a moment and erase and come back. Okay, so now we have a clean slate to start with. We want to evaluate the limit as x goes to 0 of e to the x over 3x squared. Stop the video, try this problem, see if you can evaluate the limit, see if L'Hopital's rule works. Okay, you're back. So we're working on problem 4. And the first thing I attempt is substitution to see if that easiest method will work. E to the 0, e is a positive number, it's about 2.718. And it's raised to the, anything raised to the 0 power, that's not 0, is a 1. So I get a 1 over a 0. I cannot use L'Hopital's rule on this one. So I have to evaluate this some other way. And the fact that I get division by 0 says my answer is either going to be infinity, negative infinity, or does not exist. So this problem doesn't factor. There's no way to factor that and reduce. So this is where I have to go, once I get into this division by 0, I have to go into this, look at each side of the limit. I have to look at what happens, the limit as x goes to 0 from the left. And I didn't need to put that in parentheses. And then I have to look at the limit as x goes to 0 from the right. Each of these are going to end up being either positive infinity or negative infinity on their own. If they come out the same, that's your limit. If they come out different, your limit doesn't exist because the limit on each limit coming from the left and right has to match in order for the limit to exist. So let's look at this top one first. Limit as x goes to 0 from the left. So this will be e to a slightly negative number. Now, when you have a slightly negative, let's say 0.000 a really, really, really small negative number, when you have a really, really, really small negative number, you don't get a negative value on the top. Anytime you raise e is a positive number, any base raised to, any positive base raised to a real number is always going to be greater than 0. So you're never going to get a negative value out of that, no matter which side of 0 you're on. So what you've established there is coming from the left, the top is positive. Now the bottom, you have x squared. That's always going to be positive. So here again, the bottom is positive, you get positive infinity. The same thing happens on the coming from the right. You get e to the really number that's almost 0. So you get about 1, maybe you get 0.9999999, but it's still positive. You never can get a negative value out of a positive base raised to a real number. So you get a positive here, and because that's squared, you get also get a positive, because you square a positive value, you also get a positive. Up here we squared a negative value, we still get a positive. So we get positive infinity. So the solution is the limit is positive infinity. It does exist. And if you graph that, you would see that the asymptotes both went off towards positive infinity. Okay, thank you for joining me. That's all I have for this video. Email me your questions and view the remaining parts of these videos for some other indeterminate forms. This is about all I'll hold you responsible for in class at the moment, though.